do have one of these in a dome with a couple smaller telescopes on it. It's extremely spectacular. These things can move at 20 degrees a second, so they go like that. And they're big enough in a dome that it's almost scary. So we don't move them that fast with people in there because they're actually downright dangerous if something got out of control. So we move them slowly when we're working on it. Again, same picture as before. Light comes down to the top, bounces up to a mirror here, bounces down here, and then we have a very complex instrument assembly down here. And everything you see was designed in Goleta. It's not that we don't have not invented here, because we I believe don't have not invented here. But the problem is we need so much of everything that no other vendor in the science community has ever built the kind of stuff we need. We can't get the consistency without doing it ourselves. We can't get blueprints, we can't get software, people are proprietary, they don't want to tell you how they did things, and we just can't deal with that when we're trying to run a 20-year scientific program. So the net result is a totally top-to-bottom, homegrown telescope. Question?
Could you use a number of filters on a wheel with like change over time and do it coordinating with other?
Yeah, that's exact. Could we use a number of filters on a wheel and change over time? The answer to that question is yes. There's the filter wheel right here. And there's 3 layers of filter wheels. We have 18 to 20 filters, and we have the ability to add filters. So if a new scientific program came along, we can add new filters. And if you bought 8 of them, our basic deal is somebody wants to do something new, great, but you got to buy 8 so that we can put them on all the telescopes so that we can take advantage of that. Otherwise, that telescope becomes locked down to a specific program, and that completely disrupts our plan. Okay. This is a drama picture of the 0.4, trying to make it look as big as the 2-meter telescope. That's me working on the control panel. Very undignified picture. But there you have it. And so we've had these around now for a while. We've been using them regularly. We have one on Maui that I just was working on last weekend. 2 weekends ago I was fixing it. It had needed some upgrades. And then last weekend, for most of the night, I was up getting it tuned up and operating it. But it's basically looks a little more complicated, maybe it is. But you can see this little area down here. This is chock full of instrumentation. I mean, there's no room for anything in there. It's just a great big lump of technology on the back of the telescope. This is our enclosure concept. We've actually decided to go to a slightly different enclosure. It's long enough that you can put 2 0.4s in it instead of 1. This was conceived of as we built it and you could put it in a shipping container and ship it to site completely pre-assembled, and wouldn't that be wonderful? Now this is an interesting little story about how clever thinking like that can lead you astray. If it's going in a shipping container, it can't be wider than about 7 feet 8 inches. So it's 7 feet 8 inches from that point there to that point there when the roof is closed. Well, I think you can see that it might be a little crowded inside. And this door is 30 inches tall. Well, I'm not 30 inches tall. So how do I get through this door with a back problem? So we learned a whole bunch about this, that maybe we should make it modular in 6 pieces and break it up and put it in a container. Then we could make it bigger, taller, and you could get in and out of it. So we redesigned it, and we just brought that up. I just finished getting the control system working on that yesterday. Now this has an interesting name. It's called an Aquawan, A-Q-A-W-A-N. Anyone happen to know what that word is or means? There you go. This is worth an LCO t-shirt for the first correct answer. It's Chumash, and it means to stay dry, which I thought was a really clever name. So these are known as Akawan enclosures. Here we go, we're about done. So the .4s, we've got a whole bunch of them. We're getting the programming finished. Here's third light. The first two images taken were attempts to focus. When they thought it was in focus, they immediately went to the Dumbbell Nebula and did a 5-minute exposure on a telescope that had not been polar aligned except by eye. This is an incredible image if you're an amateur astronomer and you realize the stage at which this was taken. It's, however, not a great image. You can see that we had a, oops, where'd it happened? Here you can even see either a plane or a satellite went through right here. You can kind of see it. Okay, this is one of those darn slides. As I said, we're building our own cameras. These chips are, I don't know. They're slightly bigger than a saltine cracker. How's that? But, you know, they have 92% quantum efficiency, so basically all the photons that fall on them get turned into signal that we can read. So you can't do better than 100% quantum efficiency. So this is amazing stuff, and we have 32 of these chips, and they're all the same, so that we can have this homogeneous system. And I'll skip that. There's a lot of technical detail. We also use the Santa Barbara Instrument Group cameras on the small telescopes, which is another company here that started in Santa Barbara around 1992, and they're out in Goleta. Okay, our software network. The important thing for us is there's never going to be another special purpose educational dumbed down system. We're going to do one system that the professional astronomers and the learners use. Now, we will be a little kind to the learners. We'll have some grayed out buttons, so you won't be able to start pushing buttons and get yourself hopelessly confused. But the learners will be able to start using a system that some other scientist is using at the same time. And then as the learners, if you will, learn and get more fluent and go through modules, which we'll give them online modules once they sort of show that they know what's going on, and especially if they download the images that they take and we see that they're really doing something with them, we'll make more of the buttons change to non-gray and make the thing more available all the way up to the point where classes, I mean, for instance, a class here could do a full-scale science research project at the same level of equipment, the same cadence, the same everything that professional astronomers are using. Let's see. Standard observations like, okay, I want to do a transit, I want to look at a variable star, I want to look at XYZ. We'll do all the data reduction pretty much automatically. And the reason we have to do that is not that we really want to, but we produce so much data at sites that we would be totally saturating our 15 megabit per second link coming into our building. And we can't even get all the data in a day. And of course, we can spend a lot more money on more bandwidth, but it makes much more sense to do the reductions at site and then send the scientific result down. And then you can vet it, and very often you'll say, nah, bad night, we have to do it again. So we only have to then send down the good data. We have a completely new, from the blank piece of paper, vision for how to do astronomy image processing. We have a supercomputer in Goleta, and anyone who wants to do image processing, all they have to do is have a web browser, open up IE or Netscape or Chrome or your Opera, your favorite browser, go to www.lcogt.net, log in, go to your workspace, and you now have access to, you know, about 1,000 processor supercomputer with all of your data in it ready to go. So I think that sounds neat, but you know what? The way science